My name is Tijmen Blankenvoort, and I'll be your host for this session. Who am I? Well, I'm leading a team of deep learning researchers in Qualcomm AI Research, and we are looking into the newest methods for neural network compression, quantization, and neural architecture search. But that's enough about me. Let's turn to our amazing speaker for this session. I want to introduce you to Bert Moons. Bert received a PhD in electrical engineering, summa cum laude, from the KU Leuven University in Belgium, working on chips and computer architectures for embedded deep learning. And currently, he's working with me in Qualcomm AI Research in Amsterdam, focusing on improving the efficiency of neural networks on the edge devices. And that's what he's going to talk about today, the whole pipeline of, if you have a model, how do you make it more efficient? Now, for this session, please post your questions in the chat, and I'll try to respond to some of them myself, if possible. Or if you really want to wait for Bert to answer, we'll bring up the questions at the end of the session, and I'll try to moderate that in the chat channel. Audience, please enjoy, and take it away, Bert.
Right. Thanks, Simon. So indeed, I'll be talking about Qualcomm's model efficiency pipeline and some of our research that we've been doing in trying to enable deep learning inference at the edge. So before I dive into that, let me briefly introduce Qualcomm AI Research and our Amsterdam office. So at a very high level, what we try to do at Qualcomm AI Research is to develop novel methods in perception, such as applications like object detection, speech recognition, and so on, or applications in reasoning, or actions in action and decision making. So we're trying to develop novel methods in these fields and eventually deploy them on some of our product lines in IoT, mobile, automotive, or cloud solutions. So the whole of Qualcomm AI Research is focusing on these topics in general. Then at Amsterdam, we have a new lab since a couple of years. So that part is called Qualcomm Research Netherlands. This is now a lab of around 50 to maybe 60, 70 researchers in total. And we always have openings, and we're always looking for new talented people. So if you're interested, you can always check out our careers website and search for Amsterdam. So with that, I'll move on to my agenda. So I'll split my talk today into 3 different parts. First, we'll take a look at what would be required for energy efficient machine learning at the edge. And I'll introduce a concept that I'll call the computational budget gap. And from that introduction, we'll move on to our model efficiency pipeline, which is a set of algorithms that reduce the cost of on-device inference. So we'll talk a bit about NAS, neural architecture search, which will be the bulk of the talk. And then we'll move on to compression algorithms and some state-of-the-art quantization algorithms that our researchers have been developing. After that, I'll just highlight our AI model efficiency toolkit, which open sources a number of these algorithms that are part of that pipeline. And then finally, we'll take a very sneak peek to what's next, what would be next in energy efficient AI. And we'll take a look at novel techniques that could kind of expand that model efficiency pipeline. So I'll first start with this introduction. So I think this for this audience, this slide is very obvious. So what is happening today is that AI and machine learning is becoming more and more ubiquitous. That AI is being used all around us. You have AI for speech recognition, image recognition, and so on your smartphone. There are applications in smart homes. We're now using AI for this video conferencing service. Autonomous vehicles have been growing for a couple of years. There are applications in smart factories, extended reality, smart cities, and increasingly video monitoring. So there's all these kind of applications that are very interesting and that we want to try and embed onto embedded devices and TinyML devices even. So one of the tensions there is that these neural network applications are typically huge. They're huge and they are growing fast. And to illustrate this, there's this graph here where we show how the number of parameters that are used in neural networks has evolved over time. So this graph goes way back to the 40s and 80s. But what's most important is the evolution of the last couple of years, let's say the last 10 years. And also there we see that the number of parameters used in neural networks has kind of exponentially grown over time. And this is a real challenge if you want to bring this to an embedded device or a mobile device. So there's this couple of challenges that are associated with AI workloads. On the one hand, they are typically very compute intensive. They're always growing, becoming more complicated and larger with more parameters. They have complex concurrencies. And at the same time, we want to run them in real time in a kind of always on fashion, especially on tiny ML devices. And then on the other hand, we have the constraints of our mobile environments that this audience is also very familiar with. So there's always these kind of limitations in terms of memory that is on our platform. There are thermal limitations, power limitations, and eventually also battery limitations. So it's a real challenge to bring these increasingly complex AI workloads onto our mobile devices. And to illustrate that further, we'll take a look at what I call the deep learning budget gap. So we're looking here at a very quantitative, high-level visualization of neural network applications and how many operations they would require in order to run these applications in real time. So that is what I call the computational budget. How many operations do you need on your hardware platform per second in order to run a neural network application in real time? And this is this first trend that we see happening today and that we also saw on the previous slides. So over time, these neural network applications become more and more expensive. So their computational budget requirements, they increase. Then there's a second trend where a lot of people in hardware design and computer architecture are constantly building faster, more energy efficient hardware platforms. And what they'll have is, let's say you have some power envelope available for your hardware platform. That also means that you'll have some computational budget available. And it's the innovations in computer architecture and chip design that keep on trying to push up the computational budget that a hardware platform can offer within a given power limit. And that's what we also try doing at Qualcomm, where we have different product lines that evolve over time and become more and more powerful. And what we'll see is that they basically start closing that budget gap between the application's requirements and what a hardware platform can offer. Then there's a third trend, which will be actually, or let me first look at other types of devices. So the Qualcomm Snapdragon product lines, they are mobile devices, but they're also tiny ML kind of devices that have a much smaller power envelope available. And as a result of that, we'll have a smaller computational budget. So for tiny ML devices, this budget gap between large-scale neural network applications and what their platforms can offer is still very large. So there's a third trend in which you see a lot of research. So a lot of people have been focusing not on building better and more complex neural network applications, but have been focusing on trying to make them more energy efficient. So that is what I try showing here. So over time, a lot of innovations are being introduced that push down the budget requirements of neural networks, such that you can close the budget gap. So these are a set of techniques that are kind of orthogonal to the innovations in chip design. And that is also what the rest of the talk will mostly be about. So an example of this third trend is our model efficiency pipeline. Our model efficiency pipeline is basically a set of techniques that focus on 3 different axes that you can use to shrink your AI models and run them more efficiently on hardware. A first axis here is neural architecture search, or hardware-aware neural architecture search, which we'll focus on next. But then there are also ways of pruning and model compression, and also accurate fixed point quantization, which is a topic on which our group has contributed a lot. So we'll go through each of these steps in a bit, and I'll first start with the neural architecture search topic. So the previous speaker also focused on this quite a lot. So it's really a challenge in really optimizing your neural networks for specific hardware devices. So this is kind of a problem that over the last couple of years technique called neural architecture search has tried to solve. So we're trying to find ways to automatically design networks that are optimal on your specific device. Now, let me try and frame why that is really necessary. So whenever you have a specific neural network or a specific task, if you want to evaluate that truly, you have to evaluate it in terms of 2 points. You have to measure its latency on a device. That's fairly trivial if it fits. And you also have to evaluate its accuracy. And this is very tricky typically because that would involve training that network. You have to train it typically from scratch. So if you look at the cost of training a single state-of-the-art network on a basic data set like ImageNet, we'll see that that can typically take more than 2 GPU months or an equivalent of 2 GPU months, which is very, very long and very expensive. If you would run this on a commercial cloud service, this would cost you around $4,000. The issue there is that you not only have to do this once, but you might have to do this many times actually. Train many of these networks for different hardware platforms, for different latency targets, different accuracy targets, different applications, and so on. So this really doesn't scale. We cannot spend $4,000 for every network that we want to map. So we really need a cheap, scalable neural architecture search method that is hardware aware and can really reduce these design and training costs significantly. So this is what I'll try to explain how we can solve it here at Qualcomm. So there's a lot of literature on NAS already. So there's a lot of existing solutions, but they do not really address all of the main challenges in really building a product around this. So a lot of these methods that are out there, they kind of lack a way of doing a very diverse search. So they typically cannot handle very complex search spaces with different styles of blocks, different attention mechanisms, different styles of activations, and so on. So that is really a flaw in most of the literature. Another challenge that is not typically addressed is the very high costs of a lot of the methods that are out there. So the methods that do allow a diverse search are typically very high cost, and they require thousands and thousands of hours or months and months of GPU time to actually execute. A third challenge is that a lot of the methods that are out there do not scale. So they are typically hardware aware for only a single hardware platform, for example, and they do not scale to multiple devices or different software drivers and different software versions and so on. Then a final challenge is that a lot of the methods that are hardware aware use very unreliable hardware models, simulators typically, or proxy metrics like the number of operations, which do not really correlate with actual runtime on a real device. So in contrast to that, we introduce our DONA method. So it's DONA stands for Distilling Optimal Neural Network Architectures. And this is a form of neural architecture search that is built upon the concept of knowledge distillation. And what we'll do here is that this will be an efficient NAS method where we can do hardware-aware optimization and find really Pareto optimal architectures in terms of accuracy and latency at a reasonably low cost. So DONA offers this kind of diverse search where you can search amongst different types of cell types, convolution types, transformer types, and so on. We can do it at low costs, at the cost of running around 2 to 10 networks from scratch. We can do it scalable, so we can very quickly repeat this for different hardware devices or software versions. And we can have reliable hardware measurements because we use real devices in the loop. So I'll try to explain our DONA method as a 4-step process. So what we'll try to do in DONA is we'll try to build accuracy model or a predictor of all the architectures that we want to search amongst. So all the architectures in our search space. And this accuracy predictor will actually, it will predict the accuracy of an architecture without really having to train it. So once we've built that accuracy model, we can do a search at very low cost. And so a first step in this pipeline is to define some sort of a reference model and a meta architecture and a search base on top of that. One example of how we could do that is given here. So in first phase, we select a reference architecture, something ResNet 50 like, for example, or a much larger model that is very accurate but very slow. And then we'll split that reference architecture into a set of blocks. And then in this example, we have 5 blocks in light blue. And then for each of these blocks, we'll define a search space of different instantiations of that block that we want to search amongst. So the search space, yeah, these are just examples, but we could search over different types of kernel sizes, different types of expansion rates, depths, different widths or the number of channels and so on. All of that can be searched over. So this is another example of what that could look like. So for these blocks, we can take ResNet style basic blocks. We can mix and match it with MobileNet style blocks, Vision Transformer blocks, or ShiftNets, for example. These are all just examples of what we could add to our search space using this technique. One example or 2 examples of models that this search space could generate. This is just a limited example. But if you look at the model on the top left, we have a tiny model that is optimized for a desktop GPU and achieves around 73% on ImageNet. So you see that it's very shallow and yeah, not that wide. And then there's this model on the bottom right, which is a lot deeper and achieves a lot higher accuracy. So this is just an illustration of different styles of models that we could generate in this search space. Once we have defined that search space, we will start building that accuracy predictor. So we want to predict for every model in our search space, we want to predict its final accuracy without having to train it. And for that, we rely on a process we call block-wide knowledge distillation. So I'll very briefly try to explain it, but what we'll try to do is that for every block, so we made a split in our reference model, and we'll then replace these blocks in the reference model with smaller blocks that are a part of the search space. And so for each of these smaller blocks, we'll distill the knowledge of the reference block and try to approximate its performance or its transfer function really as closely as possible by minimizing MSE loss on the output feature maps as illustrated here. And what this yields is actually 2 things. This yields something that we call a block library, where we, for every block in our search space, we now have a set of pre-trained weights through that distillation process and a set of quality metrics. So each of these blocks has now an associated value, a loss value, that is a measure of how good it actually is, how much it will contribute to final accuracy. So that is what we call our block library, the set of these 2 libraries really. Then after, we build what we call an architecture library, where we sample a representative set of architectures from our search space, and we fine-tune them using the pre-trained weights that we get from our block library. And once we have the combination of these fine-tuned architectures and our quality metrics, we can actually build a very simple linear regression model to predict the accuracy of all the models in our search space. And this is an example of how well that works. What I show on the top here in red are a comparison of a number of state-of-the-art references and how well they can actually rank models in their search space. So this comes out of a BOSNAS paper reference. So what this BOSNAS can offer is a ranking metric of around 0.65. This is a Kendall-Tau ranking metric. It might be too technical, but yeah, it's basically a metric for how well you can rank models in your search space, and 1 would be an ideal or perfect ranking. There's other methods that are more conventional, like DARTS or MNASNet or DNA, which our method is kind of based on. And for this single test set, which is based on MobileNet v3, you see that they all have they don't have very good ranking metrics, all these methods. So what Donna can achieve is much higher ranking. We can achieve 0.8 or 0.91 Kendall-Tau even on our own test sets. So that means that we can really distinguish the good models from the bad. Then as a third step, once we have that accuracy predictor, we can start doing a very quick evolutionary search. So we'll take a Snapdragon device, for example, together with this accuracy predictor, and then just execute a fairly plain vanilla evolutionary search to find a Pareto front of optimized models. And we do this more specifically like this. We have an evolutionary sampling algorithm based on NSDA2 that generates and samples end-to-end models. And then we'll transfer these end-to-end models to our target hardware and measure its latency on the one hand. And then on the other hand, we use our accuracy predictor to predict that model's accuracy and also feed that number back to our sampler. And this allows us to have very quick turnaround time. So once we have built that model, that accuracy predictor, we can very quickly do hardware-aware searches on any kind of device. And as a final step, we will also sample and fine-tune some models. So the result of step C really was a set of Pareto optimal models in a two-dimensional space. And we can now sample them and fine-tune them to full accuracy in around 10% of the time of what you would need for training run from scratch. So this is an overview of some results we can get using Donna. So what I show here is are these kind of Pareto fronts that we find through our NAS methods for different types of complexity metrics. So you can optimize for desktop GPU, for example, or for different engines on Qualcomm Snapdragon platform. And what we can show is that we can really, independent of the hardware platform, we can always find models that outperform a set of state-of-the-art baselines across the whole accuracy range, in this case on ImageNet. And so here, for example, we beat ResNet 50 by around 50%, by around 3x rather on Qualcomm's Adreno GPU. We can also compare this method to other styles of methods like OFA, DNA, or MNASNet. And I think what's important here is that if we judge these models based on the diversity that they can offer, so the different styles of network that they can handle, and then the limit of their search costs in the case where you would have many hardware platforms and software versions. We can state that we can have a very diverse search at the level of MNASNet, which is a Google reference, at a cost that is around 100x lower. So we really have a cheap and diverse NAS method here. And as a final conclusion on this topic, you can not only use this NAS method for ImageNet classification, but you can also very easily apply it to downstream tasks such as object detection. Here, all of the models in blue are Donna models, and we compare them here to a ResNet 50 based object detection architecture, where we are around 2x better than that reference. You can also look at like EfficientNet V0 based networks, where we also significantly outperform. Then you're not limited to kind of CNN style architectures, but you can also apply this method just as well to networks like vision transformers and so on, without real code changes. That brings me to the second part of our pipeline, the model pruning and compression step. This is more conventional and maybe a bit older than the whole neural architecture search field, but it's still very useful in the case where you have some redundant layers in your network that were not a part of your neural architecture search. You can always use this compression step really to further bring down the cost of your model. There are basically two approaches to pruning or model compression. A first one would be unstructured pruning, for which Song Han's deep compression paper is a prime example. This was introduced in 2015 at NeurIPS at the time. And this is a method where you would try to reduce the complexity of a densely connected neural network, as shown here in the middle, by removing unnecessary synapses or unnecessary connections, as illustrated here. So this is a process where you remove all the weights really that have a very small value, and then fine tune the resulting network. And I think they showed that you can really achieve very high accuracy without any real, with very significant reductions in complexity. The downside of such unstructured pruning is that it's really non-trivial to accelerate that on parallel existing hardware. So you need specific accelerators, specific chips really to do this. Another approach is structured compression, which typically uses low-rank mathematical low-rank approximations. So this is a set of methods for which we have a great overview coming out of our group. So there's a whole paper kind of evaluating and comparing these different types of structured mathematical decompositions. So for details, I refer the audience to that paper. But it's basically an overview and a comparison of a number of common techniques like SVD compression or Tucker-2 compression, which have been used in vision quite a lot. So as a main takeaway, I think I can show some results that we have that also comes out of this paper, where you can show and compare the performance of these different compression methods on a Resnet 50, for example. So in general, channel pruning and spatial SVD typically work best. And we can achieve around 2x reduction in number of operations at a very limited accuracy loss. That brings me to the third step in the pipeline, our quantization research. So I'm assuming also this audience is quite familiar with the concept of quantization. So typically on a GPU, all of your models would be defined using floating point numbers, and they are executed using floating point hardware. But typically on embedded platforms, you would convert those models into a quantized format, where you use fixed precision integer representations rather than floating point numbers. And we typically do that because this significantly reduces the memory usage, the energy consumption, and also the latency of your runtime on a mobile device. The effect of this, of course, if you quantize to a reduced number of bits, is that you also lose information really in your signals. And that is illustrated here on the bottom left. So where we have a single image represented either using 24 bits per pixel, 8 bits per pixel, or 1 bit per pixel. And you see that if you reduce the number of bits, you really lose information compared to a higher bit-to-bit representation. So here our team has been quite active. So there's a number of papers that are listed here chronologically that our group has been publishing. We went from data-free quantization as a baseline method and a baseline tool, where we could achieve state-of-the-art 8-bit results, to a tool that we call AdaRound, which stands for adaptive rounding, and which I'll discuss in a bit, where we could achieve state-of-the-art 4-bit results, so 4-bit weight results. And then also last year, our paper on Bayesian bits came out, which is a form of automated mixed precision. So this is a technique where you can choose how many bits you want for every layer, or it's an automated way to do that. I'll come back to Bayesian bits later, but I'll briefly discuss what we do in AdaRound, because I think it's a really cool real concept. So AdaRound is a quantization method where we do adaptive rounding. So instead of what you would typically have in traditional quantization is that you would always round to nearest. You would always round your floating point value to the nearest integer. And so what my colleagues, Marcus and Ali, actually showed is that that is not really optimal and that you can do significantly better. And for that, they generated this really cool experiment where they compare different rounding methods in terms of accuracy for a single layer in ResNet. And so they show that if you do vanilla quantization using nearest neighbor rounding, you have some 52% of accuracy. If you use flooring or ceiling, your accuracy completely degrades. But they also, and this is the interesting part, they also showed that you can actually do better than the nearest rounding. If you can just stochastically sample situations where some weights are rounded down and others are rounded up, you can actually outperform that rounding to nearest baseline. And that's also shown here on the right. So we have all of these different stochastic samples in blue, the nearest rounding in red, and then they've shown that you can actually significantly outperform it by more than 10% in this example by making the right choice. And so this paper is focused on finding a systematical way to find the best rounding choice, to round up or down. And yeah, so the question is really, can we learn this? And like Marcus and Ali came up with a very cool way to do this. So they just use a very limited set of data and stochastic gradient descent to learn whether you want to round up or down. And the way they do that is fairly simple and straightforward. So if you look at the quantization problem, what you actually want to do is you want to minimize the difference or the L2 norm between your floating point outputs of your layer and the output with quantized weights. So the W tilde here is the set of quantized weights. And so they learn whether to round up or down by defining the quantized set of weights like this. So they always round the floating point weights down, and then they add a learnable parameter which will learn to be either 0 or 1. And if you do it like this, you can just use SGD and basic optimizers in PyTorch and TensorFlow to really learn for every weight whether it should round up or down. And this leads to very good results. So what they've shown here is that using this kind of setup, using this kind of add around setup, you can achieve state-of-the-art results with 4-bit weight quantization, which is kind of significant. So another thing I really want to talk about is our open source tool. So this might also be very interesting for this audience. So Qualcomm has released an open source tool for model efficiency that we call AMET, or AI Model Efficiency Tool, where a lot of these techniques that I've been discussing have been implemented and are open to the general public. So there are two references here. One is the AMET library, and another is the AMET model zoo. So yeah, there's a link to the web pages here, and they are accessible to everyone. So yeah, the AMET library combines this kind of state-of-the-art quantization techniques with some of the compression techniques that we've been discussing earlier. The AMET model zoo is a zoo of accurate pre-trained 8-bit quantized models. So if you don't want to go through the hassle of quantizing your models yourself, you can always pick one from the library or the model zoo. And these are just as an illustration, some of the results that we get there. So both for TensorFlow and PyTorch, we have a whole zoo or library of models for classification, pose estimation, speech recognition, GANs, and so on, where the accuracy loss due to quantization is really minimized. So yeah, if this interests you, you should definitely take a look there. That brings me to the last part of my presentation. So we'll take a sneak peek of some ideas and some of the latest research that our groups have been working on that try to answer the question of what could and should be next in efficient on-device AI. So if you take a step back and look at that pipeline, there were, I guess, 3 key results that that show the limits of the current approaches. So in terms of NAS, we looked at, we saw that we could always outperform baseline models with this hardware-aware NAS approach. For example, ResNet 50, we could beat by around 3x at the same level of accuracy. But it's not that you can get 10x by applying such a NAS technique compared to heavily optimized hand-designed networks. The second step was compression, and also there we could achieve around 2x of model compression, also for ResNet 50 here, with a very limited accuracy loss. So this is also 2x and not a 10x or 100x that we might be aiming for. And then finally, there's this, we've seen that we have established baselines and developed state-of-the-art methods for 4-bit and 8-bit quantization. But the question is whether we could do better potentially. So all of these techniques are great, but they don't, in a way, they are still limited. So you can also look at it like this. So in this graph, this is a very high-level view of what I would call task quality or accuracy on the y-axis, and then throughput on the x-axis. So how many frames per second would you be able to run on a hardware device? And so we have all of these baseline models for computer vision, like ResNets, MobileNets, and so on, that would be positioned like this if you would quantize them to 8 bits. Then on top of that, we've seen that through neural architecture search and compression, we could kind of push this Pareto front of architectures, of baseline architectures, by maybe 1.2 to 3x to the right. So for the same level of quality, we could boost our throughput maybe 3x. So the question is now, what would be next? And one answer, in my view, would be to move towards mixed precision quantized neural architecture search. So not only do it hardware aware, but also bring quantization and the effects, the detrimental effects of quantization into the loop of your automated optimizations. And the reason why I think that would help is by looking at that Bayesian bits paper that also came out of our Qualcomm research groups. So what this shows here on the left is the effect of doing mixed precision quantization using the Bayesian bits method on a ResNet 18 on ImageNet. So in mixed precision, we would automatically choose the number of bits that you need for every layer. So you don't fix it to be 4 or 8 or 2 for the whole network, but you automatically design or automatically optimize the number of bits for every layer. And in this paper, we can really show that you can have around 1.5x improvement by moving from a uniform type of quantization here, like the packed reference, to the Bayesian bits optimization. So by doing this kind of optimizations, you can really benefit. And that is also shown here on the right. So what we show here is every line is a specific layer of ResNet 18, and then we show what the optimizer thinks would be the best quantization bit width. So you see that some layers are at 8 bits, others are at 4 bits, and yet others are at 2 bits. So yeah, this really leads to a large advantage compared to a uniform optimized baseline. Also on the chip level, we know that we can benefit a lot from mixed precision. And this is an old paper of mine that we presented almost 4 years ago at ISCCC, where I presented a chip or a processor architecture where you could dynamically vary the precision for every layer. And we showed and kind of measured that at the system level, you can expect around 10x improvement if you go from 8 bits to 2 bits. So this is really that we should something that we should move towards. Then there's also papers in the literature already that try and do this. So there's APQ, which was presented at CVPR 2020 last year, that showed that you can have around 2.2x in BitOps savings by combining hardware awareness or neural architecture search with mixed precision quantization. But this is what this could look like. So if you go from the baseline to the regular NAS to the mixed precision NAS, I think we can gain around another factor of 2x on the system level in terms of this Pareto optimal front. And another set of techniques that will really help and that we are moving towards is a number of techniques that can be described as running networks conditionally. So we'll take a sneak peek at some models or some neural architectures that execute workloads conditionally. And this is actually pretty obvious that you should do that. So a basic example would be in classifying images. So it's very apparent that if you look at these two images of a horse, for example, that the one on the left is a lot easier to classify than the one on the right. So there's a lot of things that you can do to actually make your networks adapt dynamically to your input data and thereby reduce their computational costs. So there's this paper that's already almost 3 years old called Multiscale Dense Nets, where they exploit exactly this. So they have this network architecture which is multi-resolution, so it operates on different scales of inputs, and it has a variable depth, really, because they place different classifiers throughout the network that can allow an early exit. So let's say if you have a simple image like the horse on the left earlier, you would take exit 1. For a harder image, you would take exit 3. So we would only need and use your compute resources when they are actually required. And that brings you around another factor of 2 to 3x in terms of energy complexity trade-off, if you can efficiently do this kind of early exiting. There are other fields like semantic segmentation or object detection where this can also be applied. So yeah, what's apparent in a lot of real applications in autonomous driving, for example, is that a lot of your image and your video streams are actually very sparse. There's not too many objects depending on the full image compared to the full image. And a lot of the image itself is actually a background. So this is also something that you can really exploit. And one example is a paper by Thomas Verelst from KU Leuven. It was also presented last year, which was a paper on dynamic convolutions. And what the paper does is it looks at an image and kind of tries to decide through a very cheap masking unit which part of this image are actually important and which parts of this image are backgrounds that are not required for the actual classification task. And so that's what you see here. You have this image of a bird, then a masking unit that decides which pixels in yellow are actually required. And so the real baseline network, the backbone here, is only executed on the yellow pixels. And this can dynamically reduce your compute requirements significantly as well. Another final use case is in video processing. Also there, if you think of a real application where you would have some video stream you want to surveil in some sense, it's actually quite apparent that these frames don't really change that much. Here in this image, the cars might move, but a lot of the backgrounds and roads and so on, they're actually fixed throughout your frames. And this is something that the Qualcomm research team is really focusing on. So there are 2 papers I'll briefly highlight from our groups that really exploit these features of these video streams in a very efficient way. So first one is skip convolutions, which will be presented, I think, next week at CVPR 2021, which is a very cool paper where instead of executing neural networks on full frames, we execute them on a residual frame. So you take the difference between 2 frames and then kind of use a learned skipping gate to decide which areas of this frame are novel or interesting enough to actually compute on. So that is what is shown here. So only the blue pixels are computed, and the other pixels are taken from the output of the previous frame. And also here we can gain like 2x, 2 to 4x, depending on the complexity. And the final example is a video classification example, also coming out of our groups in Amsterdam, where we do a form of conditional early exiting for video recognition. So also in video recognition, it's apparent that some videos are just easier to classify than others. So rather than looking at all the frames constantly, you could conditionally look at frames and use a specific policy function and gating mechanism to do early exiting. And also there, you can have very significant gains up to 2 to 4x on the system level. So if you combine all of that, we have this baseline Pareto fronts, we have regular NAS, mixed precision NAS, and then finally conditional computing. We can, if you combine all these techniques, which are kind of orthogonal, we can get to this 10x improvement over our baselines. So that leads me to conclude, Tijmen. I hope I'm not going over time. So I talked about energy efficient machine learning and the budget gap. I talked about our model efficiency pipeline, neural architecture search, compression, quantization, and how we are open sourcing those tools and techniques through AMET. And then we had some thoughts on what could be next in energy efficient AI. So are there any questions? And do we have time for questions?
Thanks a lot for the presentation, Bert. Excellent talk. I hope everybody is now excited about deploying their models to devices and doing so with neural network architecture search tools and quantization tools. I have a couple of questions from the audience. One from Akram Bahar Louis. Is AI on device always going to be inference? And what are the challenges to do on device training to some extent?
Yeah, so yeah, you could always, the AI on device is not always going to be inference. You could also do on device training, of course. It depends a bit on the number format that you can use. So on if you have a fixed precision device, it's typically very hard to do accurate training, and that is an active research topic on whether that's even possible to do training using fixed point number formats. But if you have a floating point mobile device, you can always write the libraries to do training there. So there's no specific challenge there, I guess. Yeah.
Right, awesome. One more question from Yunjie Pan. I wonder if mixed precision models could be implemented on general purpose processors. Is that something that's doable?
Yeah, it depends a bit. So there are multiple strategies, I think, and it depends also on how much gains you want to get. So one thing that could be trivial is that you would, if you have, for example, 2 or 4-bit quantized networks, that you would force your software to only use the MSBs of an 8-bit or a 16-bit word, and then you can just run this on a general purpose processor and get the energy benefits. But if you really want to accelerate and kind of pack your data closer together at lower bit width precision, then I'm not sure if this would be supported on a general purpose processor.
Yeah, right, excellent. One more question from Guangyuan Hu. For deep learning benchmarking with GPUs on Qualcomm supported platforms, such as Samsung phones, are there any development tools available for researchers to run set things on, let's say, a GPU, for example?
To run things on a
Qualcomm GPU on a Samsung phone, for example, yes.
I'm not too familiar with with what is out there for the open community.
For example, the Snapdragon neural processing engine, one might imagine.
Yeah. Okay, so that is fully available. Yeah. So there is the Snappy, what we call Snappy, which is a tool set to map neural networks on device. Yeah. Snapdragon neural processing engine. Exactly.
Engine, yes. Look it up and use it so you can deploy all your models to Qualcomm mobile devices. I think that's it for the questions. We're also a little bit over time, but that's fine. We just ate up people's breaks a little bit. Right, again, thanks a lot for the presentation, Bert. I hope everybody enjoyed that.
This would not be made possible without our sponsors, whom I would like to once again express our gratitude, starting by premier sponsor Newton.ai. Thank you guys so much. The executive sponsors, which involve ARM, Edge Impulse, Qualcomm AI, and Sentient. The platinum sponsors, which involve Infineon, Reality AI, the gold sponsors, which involved Latent AI, SenseML, and last but not least, our silver sponsors, which involve EMSA, Greenwaves, Kixo, Imagimob, HOTC, Seed Studio, and ST Microelectronics. Thank you, everybody. See you all tomorrow with more exciting features.